Okay, evening everybody. Can you hear me okay?
Yep, I can hear you fine, Brian.
Great, that's fine. Numbers are building up to 24 online. Okay, thanks guys. Just wait until the hour clicks over to a minute past. Oh, it's just gone, and we'll get going. So good evening, everybody. My name's Brian Lawson. If you dialed in for the first time or connected in for the first time, you won't have met me. But if you've watched the previous ones, it'll be, oh, I've heard this before. I'm the technical director for Projex Solutions. We're a project management and engineering services company based in West Yorkshire, and we've got an office up in Teesside as well. We're hosting these lectures to support the West Yorkshire area IMechE committee. It's a series of STEAM lectures, or this is the fourth in a series of 8 STEAM lectures, and the subject is condensate management. This series has been run in collaboration with the University of Huddersfield, so thanks to Josh and Carl from the engineering department there in Huddersfield. The lectures are aired over Teams and presented by our Dan Wells, who is the National Consultant Specialist working for Spirax Sarco Ltd. In a moment, I'll hand over to Dan. Just some basic logistics. The presentation will last about 50 minutes. There will be an opportunity for Q&As, for questions and answers at the end. But if you use the chat function, I believe you can see at the top on the bar, there's a Q&A chat line. If you do have questions, feel free to use that. If they do come through during the presentation and it's appropriate, I'll maybe just interject and we can get Dan to answer it there and then. So without further ado, I'll hand over to you, Dan. Cheers.
Great, thank you so much for that introduction, Brian. Thanks also to the IMechE, and thank you to the University of Huddersfield for arranging this suite of presentations. And as Brian mentioned, we have introduced ourselves in some considerable detail in the previous presentations. So please excuse me if I don't labour the point of who Spirax Sarco are as an organisation. I've also laboured those very, very useful resources and tools that we've got available on our website. I've mentioned how those calculators and configurators are of particular interest for design purposes. You know, if we know how much heat energy one of our processes requires, we know how much steam, and then we can size the steam traps, the pipework, and so on and so on. But another reason that those calculators are so important to us is in helping us to calculate our cost of steam. And I really, really can't labour the importance of understanding what that may be. Simply put, if we've calculated our cost of steam, whenever we're able to engineer improvements or whenever we're able to apply best practice to maintain a steam-based infrastructure and reduce any losses or inefficiencies, we can calculate what that payback is, both in terms of the energy we've saved, in terms of the carbon emissions that are no longer going up the stack, and in terms of how we've been able to reduce our cost of gas and cost of water. Now, this is of particular importance to today's presentation for reasons that I'm going to go through in the coming slides, calculating the cost of steam. And we calculate the cost of steam by firstly understanding the cost of gas, and we appreciate how that's varied over the previous 5 or 6 years. In many cases, the cost of gas has as much as tripled, which obviously means that that's had an impact on the cost of steam. It's then understanding the cost of water, the cost of chemically conditioning the water, the efficiency that the boiler combusts gas at to produce steam, and the biggest one of all is the temperature of the water that goes into the boiler. So please do bear that in mind as we go through today's presentation. Brian mentioned it was the 4th presentation in the series. It's actually the 5th. I've obviously made a significant impact on the previous 4, Brian. So last week we looked at the topic of heat exchange. The week before that we looked at steam trapping. Prior to that, we looked at the best practice we need to employ when we're moving that steam from the point of generation to the point of use, which could be thousands of meters away. And then when we met in person at the university a month ago, I believe it was, we looked at the basic fundamentals of steam. So in today's presentation, we're going to focus specifically on what we do with the condensate when the steam's given up its heat energy. Condensate management, as far as I'm concerned, this is actually one of the most important and overlooked aspects of a steam loop. Yes, we mentioned that heat exchange. That's the reason why so many of our steam using clients are going to have steam on their facility in the first place. We mentioned that steam trapping, in my opinion, is one of the most important components, because if we're not trapping the steam correctly and allowing the condensate to drain away at the appropriate rate, that could be a barrier to heat exchange. It means the steam's going to be wetter with less energy present within it. So we're going to have an increased inefficiency, and we're also going to have a higher burden of maintenance. But I really want to focus on what's happening on the wet side downstream of the steam trap in this presentation. So as previously, if you would like a PDF of the slide deck, if you would like an attendance certificate, please do reach out to me personally and I can make that happen for you. But also, please, any questions we've got, do drop them into the chat function. We'll either address those questions at the end, or if pertinent, Brian will shout out and ask those questions on your behalf. So there's a lot to go through in this presentation. One of the first things really to cover off is that dreaded slide that I keep on harping back to. The steam tables. They bring together all of those relationships. Pressure temperature relationship, the pressure volume relationship, the energy that the water needs to contain before it's going to boil off, generate steam, the energy we need to add to the boiling water in order for that to happen, the total heat energy of the steam. So the steam tables really demonstrate how all of those relationships and values change as we manipulate the pressure, whether that's the pressure of the steam in the boiler, in the pipework, or at the heat exchanger itself. And we also remember that when steam gives up its heat energy and condenses, when the total heat energy shown in this column, when that hits the heat exchanger, the steam gives up its heat energy and it condenses. It changes state from gas to a liquid. But when that happens, it's the energy that's demonstrated in this column, which is exactly the same as the energy that we put into the boiling water in order to fully evaporate and change state to give us steam as a gas. That is the energy that moves across the thermal barrier and is added to the process. In other words, we can think of that as the useful energy that the process is capable of using. So when we take the useful heat energy away from the total heat energy, the energy that is left behind and retained within that liquid condensate is exactly the same as the energy that the water needs to contain before it's going to hit the boil. So obviously, if we're able to recover and return as much of that condensate as we can, get that back to the boiler house, this is giving us a really, really good head start in helping us to generate steam quickly and with a minimum of energy input in the form of natural gas, which means that not only are we reducing our cost of steam and cost of gas, but those carbon emissions are also going to be reduced. And that's really why I mentioned that one of the key and important variables is the temperature of the water that is going into the boiler. How do we keep that water at a high temperature? By recovering as much of the condensate as we can. Okay, so when we put a kilogram of water into the boiler, a kilogram of water is going to boil off from a liquid to steam as a gas. It's going to have the same mass. It's going to be a kilogram. Obviously, that means that its volume's changed. The volume of the steam is going to be determined by the pressure that we're generating the steam at. But the mass remains the same regardless of the volume. And then when that steam gives up its heat energy and condenses, its phase changes again. It's changing from a gas back to a liquid. And again, the mass remains the same. The only variable is the volume that the steam exists at. And that is dictated by the pressure that the boiler's operating at. And that's really is one of the reasons why we always refer to a system by a mass flow rather than by a volumetric flow. The volume will change, but the mass will remain constant regardless of the state and regardless of the operating pressure. So I've also gone through that pressure volume relationship. Water as a liquid, it's a single phase non-compressible liquid. So a kilogram of water, 0.001 cubic meters. It boils off to give us steam as a gas. It's expanded by 1600 times. So that's one of the reasons why we like to generate steam at a high pressure. High pressure, small volume, a lot of motive energy to move the steam around the infrastructure. But crucially, it means because of a high pressure and small volume, we've got a small cost-effective infrastructure, which is useful, especially when we're moving that steam thousands of meters around site. And then for reasons we've gone through in previous presentations, we depressurize the steam as close to the point of use as possible. One benefit, it means the steam's going to move in accordance with the pressure drop around site. We don't need to pump it. We can keep the infrastructure small by reducing the steam at the point of use. We can manipulate the pressure to control the temperature. But it also tells us that by depressurizing the steam, it's going to expand, and therefore we can get it across the heat exchanger surface area very quickly. But we need to remember that when we've depressurized the steam, it is going to want to expand. So the pressure volume relationship really tells us that if we know the pressure of the steam, we know the volume it's going to occupy. Now, what we need to remember is in previous weeks, we've discussed how steam traps, they can and they will fail, especially if they haven't been sized, selected, installed, or maintained correctly. But when we get a failing steam trap, it means that we're going to have pressurized steam that could fall in pressure as it moves across the trap. And that could expand to a factor that we don't understand or can't control. That's going to want to expand into a much smaller infrastructure because after all, condensate as a liquid is a single phase non-compressible fluid. So if that steam expands into a very, very small infrastructure, we're going to get a huge expansion that we can't control that will result in a lot of damage. And that's one of the reasons why we need so many of those steam vents that we've mentioned previously. And again, in previous weeks, I've mentioned that pressure temperature relationship. At 0 bar gauge, we know that water boils at 100 degrees and therefore the temperature of the steam is 100. But when we're generating steam under pressure, for the benefits we've already discussed, the steam's going to exist at a higher temperature. Now, we've also mentioned that when steam condenses, it gives up its energy, it changes state from a gas to a liquid, but it doesn't cool down. So there's a pressure temperature relationship that applies both to the steam and to the condensate itself. So if you think about that steam distribution pipework, if we're distributing steam at pressure, 10 bar gauge, the temperature of both the steam and the condensate is going to be 184 degrees. Now at that pressure, condensate can exist as a single phase, non-compressible liquid quite happily. But if we depressurize the steam, and if the steam trap is failed in the open position, then both the steam and also the condensate is going to need to depressurize at the same rate. So let's think about a steam trap that's depressurizing or a steam trap that's failed open at 10 bar gauge. If the steam and also the condensate is depressurizing from 10 bar gauge, 184 degrees, to 0 bar gauge, we can see that the steam, and especially the condensate, it can only exist at 100 degrees. It means that the condensate has got to cool down by 84 degrees. It's got to give up a lot of energy. And the only way the condensate can do that is by changing state from a single phase, non-compressible fluid, and expanding to a factor of more than 1600 times. So two things happening with those vents. We've got the steam that is passing across the trap and expanding. And we've got the condensate that is passing across the trap, depressurizing and expanding to an even greater factor, possibly as high as 1600 times. So of course we've got to vent that expansion away so we don't get damage imparted to the infrastructure. The problem is, whilst that steam is being vented into the sky, we're not recovering the condensate. We're not getting as much hot water back to the boiler house. So we've got to consume more cold water from the mains. We've got to chemically treat that cold water, and we've got to elevate it up to, in the case of a 10 bar gauge boiler, we've got to elevate the temperature of that water up to 184 degrees. So of course we've got to consume more gas, and our carbon emissions are going to increase significantly. So please do remember that those vents are an important and significant telltale in helping us understand the overall health of the wider steam trap population, but most importantly, the efficiency at which we're producing steam and consuming gas. So the question really is, where is condensate formed? Simple answer is, well, condensate's formed wherever there's heat loss. So the two key areas where we're going to get heat loss on a steam system, it's on the distribution pipework. First of all, we know that if we're generating steam at a high temperature and a high pressure, 10 bar gauge, 184 degrees, we could be distributing that steam thousands of meters around site in a carbon steel infrastructure. Some of that infrastructure could be outdoors. We could have missing or damaged insulation, and it could be raining. That infrastructure is essentially an oversized radiator. Of course, we're going to get heat loss. We're going to get more heat loss if we've got especially wet steam. Drier steam isn't going to condense as readily in the infrastructure. The question is, how much condensate do we need to remove? Now, we could go back to first principles and calculate the heat loss of the pipework and each individual component. In reality, we're not going to do that. It's a pretty thankless task. In reality, we're going to apply a rule of thumb, and that rule of thumb states that approximately 2% of all of the steam that is generated is going to condense out in the infrastructure before it gets to the point of use. So if we're generating 10,000 kilograms of steam per hour, we expect 2% or 200 kilograms of steam to condense out in the pipework. And that 2%, that 200 kilograms, it can then help us to determine the size or the capacity of the steam trap and where we need to locate them. And it will also help us to size the condensate return infrastructure as well. Now that's what we call the running load. And the running load assumes that the infrastructure's nice and hot 24/7, 365. In reality, the boiler is going to be switched off for certain periods of the day, or the steam infrastructure to different buildings is going to be isolated for different reasons. So we need to take into account what we call the warming up load. And the warming up load assumes that in the first few moments, more and more of the steam is going to condense in the pipework as it gives up its energy to the infrastructure. It's only for a relatively short period of time, maybe an hour or so, but it's vitally important that we take that increased condensing load into account as the infrastructure is warming up. That's the information that we size the steam traps on. The rest of the condensate, well, that's going to exist at the point of use, at the heat exchanger. So it's a significantly greater mass of condensate that we need to remove. And that's a good thing, because that's where we want the steam to condense. But we need to apply that same rule of thumb, that warming up load, because a heat exchanger, it's a huge chunk of metal. If we're warming a heat exchanger, a process up first thing in the morning, more and more of the steam is going to condense as it warms up the heat exchanger itself before it imparts any heat energy to the process. So we need to get that condensate away really, really quickly, because condensate as a liquid, we know it's the same temperature as the steam. It's just got far, far less energy in it. So as far as the heat exchanger is concerned, we might want to apply an even bigger diversity factor. We might want to not just multiply the capacity of the trap by 2, we might want to multiply the capacity of the trap by maybe 3 times, just to guarantee that we can get that barrier to heat exchange away very, very quickly. So I've mentioned that rule of thumb, factor of ×2, maybe even ×3 at a process. But that really is a rule of thumb. And if we know for a fact that we've got excessively wet steam, if we've got undersized pipework, or if we've got poor, damaged, missing insulation, then that might be on the low side. We might need to allow a little extra capacity in the trap. So a lot of steam using sites would have had an infrastructure that was designed and engineered 40, 50 years ago, maybe. And at that time, water was plentiful. Cost of energy, the cost of gas was low. No one had heard about or cared about carbon emissions. So we lived with a certain degree of inefficiency for the simple reason that the payback in the insulation wasn't that great. But of course, we appreciate today that if we can insulate an infrastructure and reduce that heat loss, we're reducing our energy bills, we're increasing the mass of steam that's available, and of course, we're reducing those carbon emissions. The byproduct is also that by having drier steam, we're minimizing the burden of maintenance through reduced erosion, corrosion, and water hammer. Today, we all appreciate the benefits of double glazing, and we appreciate the benefits of lagging our loft space at home. And the same principle applies with the steam system. It's a very, very attractive payback for us to consider. So we spoke about heat exchangers in the previous presentation in some detail. We appreciate that when we're talking about heat exchangers, it's a very broad terminology. A heat exchanger can be used to describe really any piece of capital equipment where the primary energy source, in this case steam, it doesn't come into contact with whatever it is that we're wanting to heat up, whether that be water, air, or any other process fluid. And this is what we refer to as an indirect heat exchange. Because of that reason, the steam indirectly heats up the process. There are certain direct processes we can think about. Humidification would be an example. Or if we're using a sparge of steam to heat up a tank of water, that would be an example of a direct process. When we're talking about direct processes, the steam, and most importantly, the condensate, that becomes part of that product or atmosphere. In other words, we simply don't have any condensate to return or recover. So for that reason, for the rest of the presentation, I'm really going to focus on those indirect processes where we do need to return the condensate. And if we don't return the condensate, we appreciate the adverse effect that it can have, not only on the process itself by becoming a barrier to heat exchange, but also the effect it can have on inefficiency and maintenance demands by allowing to be backed up into the distribution pipework. So those dreaded steam tables again, I keep coming back to them. You'll be sick of the steam tables by the time we've finished this series of presentations. I've mentioned previously that the steam tables are only 100% accurate and reliable if the steam is kept in a perfectly dry condition. Now, for reasons we've gone through in previous presentations in the series, you'll appreciate that it's nigh on impossible to guarantee that we've got steam that sits on that red dry saturated steam live all of the time. It's simply impossible because the boiler cycles, it's going to operate at different pressures, there's going to be different demand loads and so forth. So it's a very, very extreme example, but if we had steam that was 100% dry, we could rely on these values with 100% accuracy and reliability. If the steam was 50% dry, 50% wet, there'd only be 50% of the useful heat energy present within the steam. That could mean two things. It could mean that we got very, very wet steam, perhaps as a result of poor boiler control or poor condensate removal from the infrastructure. But because the steam was significantly wetter with less energy contained within it, it would mean that either the heat exchanger was undersized and we couldn't get the amount of heat required by the process across that thermal barrier at the appropriate rate. Or it could mean that the boiler has to work significantly harder to produce twice the mass of steam that was expected because there's half as much energy contained within it. So if we'd started off by calculating our client's cost of steam at the very, very beginning, if we now know that that steam is significantly wetter than expected with half the energy present that we were expecting, we now appreciate that we've got to produce twice as much steam. So of course, our cost of gas, our cost of steam, and our carbon emissions are going to increase significantly. But it also means that perhaps we've made the mistake of undersizing the steam trap. Because if the heat exchanger needs to consume twice as much steam, the byproduct is also going to be twice as much condensate. So we need to make sure that the size of the steam trap, the capacity, and the capacity of the condensate return infrastructure, it's actually been sized to accommodate the mass of condensate, which is in turn based upon the condition or the quality, the dryness of the steam that the boiler is producing. Okay, so we know the benefit of recovering that condensate. It's high temperature hot water. It's a byproduct at the heat exchanger. We need to get rid of it quickly because it can be a barrier to heat exchange. And we need to get it out of the infrastructure quickly as well, because if not, we're going to get steam that is deteriorating and degrading. But it can also be a burden of maintenance if we're not getting the moisture out of the steam. But if we can get it back to the boiler house, we know that there's a huge, huge benefit in putting that high temperature hot water back into the hot well. So it's there on standby for whenever the boiler needs to produce steam. The question we're often asked is, how much condensate am I actually returning or recovering? Quite often, if we ask that question of our client, in almost every case, they will say, we're recovering all of it. We're recovering all of our condensate. They often vitally, significantly overestimate the mass of condensate that is recovered and returned. Now, we can't meter that condensate because we know that if we've got a fluctuation in pressures, the result is we're going to get some steam that is evaporating, boiling off, and therefore we've got differing masses and volumes. We can only really meter condensate when it's in its single phase liquid state. It's far, far more efficient to actually monitor the condensate return chemically. The reason is boiler guidance best practice. It dictates that we need to monitor the chemical composition of the water in three key areas. It's the chemical composition of the condensate that's being returned to the hot well, any makeup water that's coming from the water treatment plant to make up any losses through inefficiencies like failed steam traps, and then the chemical composition of the feed water as it's taken into the boiler. So if we're monitoring the chemical composition of the water in those key areas, which boiler guidance best practice dictates that we need to do on a daily basis, well, we can use the formula shown at the bottom of the screen to help us calculate a ratio or a return percentage. So the simple reason is that condensate has already been chemically conditioned. So it's in a fantastic condition for going straight back into the boiler without the need for us to add any further chemicals to it. So the first thing we want to do is to calculate that percentage. For example, if our client is generating 10,000 kilograms of steam per hour, and we've calculated that percentage at 60%, it tells us that we've got 4,000 kilograms per hour of condensate that's going missing somewhere. The question is, where is it going missing? And the next question our client asks us is that good? Is that bad? Well, we don't know, because we don't really know what our client is using their steam for unless we've had the benefit of walking their plant to become familiar with their processes. If our client's got a significant number of direct steam usage points, if they've got a lot of humidification, or if they're heating up a lot of tanks through direct steam injection, then, as we've mentioned previously, there isn't going to be that opportunity to recover any more condensate. If they've got 100% indirect heat exchange systems, then we'd like to think that we could recover all of that condensate. It's a little bit more tricky than that, because we know that our client is highly likely to have a number of steam traps that maybe failed in the open position. We know that we may need to vent condensate away if it becomes depressurized and expands significantly. We know that we may have the occasional leaking steam valve or pinhole in pipework, for example. So it's fair to say that in the vast majority of applications and cases, we can work on a rule of thumb that says we should really be looking to recover about 85% of all of the steam that is being generated in the form of recovered condensate. So if we're generating 10,000 kilograms of steam per hour, we'd like to think that we're in a position to recover about 8,500 kilograms of condensate. So I just want you to look at that rule of thumb. If we're able to increase the condensate return from 60% to 80%, then it means that we don't need to consume as much water. And a lot of sites have got water scarcity KPIs, so that can have a huge benefit. And we then don't need to chemically condition that water. And if we're getting more water back to the hot well, if we can increase the temperature of the water that's held in storage in the hot well by 6 degrees up to a maximum of 85 degrees, then the benefit is going to be approximately 1% on fuel cost savings. So one of the most beneficial and efficient things we can do is it's ensuring that we get as much of that valuable high temperature hot water back to the boil house that we can. So we mentioned steam trapping when we met 2 weeks ago. The steam trap, it really is that interface, the barrier between the steam, the gas, the useful heat energy. And downstream of the steam trap, we've got the condensate, the liquid, the byproduct, far less heat energy, but it's still high temperature hot water. So I'm not going to labour the point of the importance of that steam trap selection and also the steam trap sizing. If the steam trap fails in the open position, well, sooner or later we're going to find that the steam and also that condensate is lost to the atmosphere. If it's in the closed position, the condensate can't get away, it's going to back up, and it's either going to flood the heat exchanger, which we're going to know about reasonably quickly, or it's going to back up and it's going to flood the infrastructure. And that's when the effects are going to creep up on us slowly over time. So steam trapping is vitally important. And for that reason, we want to ensure that we've got a periodic steam trap survey. Steam trap survey really means that an engineer will walk the plant He'll identify, locate, tag every steam trap. Has it been selected correctly? Is it the right type of steam trap? Has it been sized correctly, installed correctly? Is it failed open, failed closed? What's the impact on the cost of steam, the energy loss, the carbon emissions? What's the payback going to be? What we don't have control over is how quickly, or even if our client is going to replace and take that remedial action at all. What's becoming more and more important and of more interest to our client, especially as energy prices increase, is some form of instantaneous digitalization, so they can act on that inefficiency in real time as that failure occurs. And in many cases, even monitor a component as it's starting to fail, so they can plan and schedule the appropriate maintenance. So onto the infrastructure. The pipework that is bringing the condensate away from the heat exchange process itself to the steam trap. At that point, the condensate has not depressurized. So the mass of condensate, the temperature and the pressure of the condensate is going to be exactly the same as the mass of steam and its pressure and temperature. The only real difference is its energy content. Now, we need a pressure drop across the trap. So the pressure within the heat exchanger or the pressure within the steam pipe itself, that is what is going to determine the rate at which the condensate moves across the trap, the differential pressure. This example, I'm showing a differential pressure of 7 bar gauge to 0 bar gauge, just for ease of demonstration. The mass flow rate that we need to get rid of, the duty of the heat exchanger, 100 kilograms per hour. So at this point here, that condensate's under pressure. So it can and will exist as a single phase, non-compressible fluid with a very, very small volume. The problem is, as that condensate depressurizes when it moves across the trap, that's when we're going to see that high energy content needs to be given up. A certain mass or percentage of the steam, of the condensate is going to boil off, change state back to steam as a gas, and that factor of expansion downstream of the trap is going to be significant. So of course, we need to vent that away. If we're not venting that expansion away, then we're going to get significant damage imparted to the infrastructure itself. That expansion means that we could have a lot of knocking, banging, or damage in the infrastructure. But it also means that that expansion can place an unnecessary back pressure on that trap that is a further barrier in allowing the condensate to drain away at the appropriate rate. So it's critically important that we think of condensate as a biphase. Condensate is only ever a single phase fluid at a stable pressure. So the table over here at the right-hand side of the screen, it's really demonstrating visually how we need to size condensate pipework whenever it's downstream of a point of depressurization. So first of all, we take into account the mass flow rate, and then we take into account the depressurization. So the dotted line shows you how we correctly size a condensate pipework. If we'd assumed that it was a non-compressible fluid at all pressures, then we wouldn't have allowed for that expansion to take place, and the pipework would be significantly undersized. This is a very, very common error, especially if we're working with engineers who may be far, far more familiar with water-based systems that haven't allowed for that phase change. So downstream of every steam trap, of course, we need to ensure that every process has got its own dedicated steam trap, but there's no reason why those steam traps can't converge in one common infrastructure. They can, providing that we've allowed for the condensate infrastructure to step up in size, not just to accommodate the increased liquid mass of the condensate itself, but also to accommodate any expansion as a result of the condensate that's going to boil off and expand. Again, you can refer to that confusing formula I've put at the bottom of the screen in order to calculate that, or you can refer back to those calculators that we have on our website. The main thing to account for is that we've allowed for not only the mass flow increase, but also the volumetric increase of that flash steam. Now, we have also mentioned that in certain cases, the condensate will be brought back to the boiler house under pressure. If there's enough residual pressure in the condensate pipework, the condensate has generally got its own motive energy. But it means because of that pressure drop within the system, we need to allow for that flash steam, that larger volume to exist. But on those occasions where we need to pump the condensate back, whether it be electrically or mechanically, we can only pump the condensate as a liquid. So we need to vent that steam away. So there is going to be a slight inefficiency we need to take into account there. One of the benefits is if we vented that flash steam expansion away, the condensate is reverted to a single phase non-compressible fluid, and we can bring the condensate infrastructure back, maybe thousands of meters, in a much, much smaller pipe size. What we don't want to do is we don't want to see pumped condensate lines and pressurized condensate lines coming together, because it's at that point that we don't know the extent of the mix of mass, pressures, temperatures, and expansion. And that could create further damage to the infrastructure. So I want to come to a concept, an issue that we refer to as stall now. So I contradicted myself a little bit last week because I mentioned that there's actually more heat energy present within steam at lower pressures than there is at higher pressures. So when we look at heat exchangers, we want to condense the steam at the lowest pressure we possibly can to squeeze out the maximum energy content from that steam. Unfortunately, we're going to need a pressure drop across that steam trap in order for it to work efficiently. So in certain applications, especially those that are working on relatively low pressure, low flow applications, it may mean that we've no longer got enough motive pressure within the heat exchanger itself to push the condensate across the steam trap. For example, if we're condensing steam at 0 bar gauge, 100 degrees, if we've got a back pressure in the condensate infrastructure, it may well be that we don't have enough pressure in the heat exchanger to push the condensate away. The condensate is going to back up, it's going to flood the pipework, and we're no longer getting the heat exchange that we are hoping for or expecting. So we can calculate the likelihood of stall occurring by going back to what we call a stall chart. You remember in previous presentations that we've got that pressure temperature relationship with both steam and condensate. So we can plot both the pressure and the temperature on this curve. For example, if I choose 100 degrees, you'll notice that the temperature is exactly the same as the pressure. 100 degrees, 0 bar gauge. So the first thing that we want to do when we're calculating the risk of stall occurring is we want to look at the process conditions. For example, if a heat exchanger's working at 100% load, it could potentially need to elevate water from 25 degrees to 75 degrees. If the water's coming onto the heat exchanger at 75 degrees, we don't need any steam. So that's dictated as being a 0% load. We plot the temperature and pressure from one side of the curve to the other. The next thing we want to look at is the demand for steam. So at 100% load, where we need to heat the secondary side from 25 to 75, we may need steam at 180 degrees, 9 bar gauge. When we don't need to add any steam to the heat exchanger, the demand for steam is 0, so you can see the 2 points taper down. We then plot the back pressure. It's really the lift that is present within the condensate infrastructure. Useful rule of thumb to bear in mind is that 1 bar gauge steam pressure can lift a column of condensate vertically 10 meters. So if we've got a 10-meter lift, we could express that as being a 1 bar gauge back pressure. So where the two lines converge, that tells us that this is the point where we don't have enough motive energy to get the condensate out of the heat exchanger. That's a stall point of 41% load. That's not going to mean a great deal to most engineers. But if we can calculate the point at which the stall point intersects the process line, then we can convert that to a temperature. So when the temperature, when the return temperature on the secondary side increases to 52 degrees, the demand for steam falls to a point where we no longer have enough motive energy to move the condensate across the trap. So when the process condition exists within that yellow triangle, it tells us, well, we know for a fact that the condensate is going to back up and result in a number of inefficiencies and problems with the process. The question is, what do we do about it? Because when the process occurs in this area, a steam trap is not going to be suitable. Well, that's when we can move towards what we call an automatic pump trap. It's basically the big brother of a float trap. A float trap needs a differential pressure across it. When we don't have that differential pressure, the float trap will flood. It will operate a little mechanism within the body of the pump, and it will call for an input of high pressure steam that exists ahead of the pressure reducing valve or control valve. We're borrowing a very small amount of high pressure steam for motive energy purposes to shunt the condensate away. But it guarantees two things. It guarantees that we can now size the heat exchanger, so we're condensing the steam at a very low pressure, low temperature, and doing so efficiently. And it guarantees that we can get that high temperature condensate back to the boiler house where we can reuse it as quickly and as efficiently as we possibly can. Of course, there are certain areas where we're never going to have enough motive energy present within the steam. We need to pump it in some way. And we can do that mechanically. It's basically the big brother of that automatic pump trap. We're using steam to pressurize the condensate. So there's no electrical installation required. But the pump takes time to pressurize. So it's actually only going to be discharging condensate 25% of the time, because the rest of the time it's either filling the pump chamber, pressurizing it, or discharging that motive steam to atmosphere. Works like your toilet system at home. It's slow to fill, rapid to discharge. I think the downside really is that it means that discharge pipe work, it needs to be sized so that it's 4 times greater than the pipe work that's filling the pump. So again, if we'd got an installing engineer that wasn't familiar with the complexities of the steam and condensate loop and best practice, if they'd sized the filling pipe work the same size as the discharge pipe work, we're going to have a barrier and the condensate is going to back up. Alternatively, we could use an electric condensate receiver. We do need electrical installation, and those electric centrifugal pumps, they can only move condensate when it's a single phase non-compressible fluid. Any steam that's present, or if condensate exists at a higher temperature, it will result in cavitation and failure. When that happens, the condensate is going to back up, going to be discharged to waste down those overflow pipes, and we're losing a significant amount of energy. So our cost of steam, gas, and our carbon emissions are going to increase significantly. So it's vitally important that that receiver's sized, not just on the mass of condensate that's going to be produced. And remember, that's determined by the dryness of the steam, but we also need to allow for that condensate to fall in temperature, fall in pressure, so that it can cool down where it's not going to create a problem for those pumps. The good news is once that condensate's cooled down, we can bring it back to the boiler house in a much, much smaller single phase pumped infrastructure than one of those mechanical pumps. But of course, the only way we can allow that condensate to cool down is by allowing the pressure drop and the steam that is going to, the steam that is going to be produced to expand and to be vented away very, very quickly. So we need to allow that expansion to take place. Of course we do, but there's no reason why we can't recover the heat energy from it. The question we want to ask ourselves is, first of all, the mass of condensate that we're talking about and the extent at which that condensate is depressurizing, because that is going to tell us the mass, the volume, and the energy content of the steam. We then want to ask ourselves, is there anywhere else that we can divert that heat energy to? Can we use it in another process rather than vent it away? This shows you the example of what we call an in-step process. I think it's fairly self-explanatory. The high temperature, high pressure condensate, as it depressurizes across the trap, it's going to expand. That steam expansion is then taken away across a flash vessel and diverted back to the same process where it can be reused, for example, as a preheater. In other processes, we can take the flash steam that is produced as a result of that condensate depressurization, and we can divert it back to a completely different, unrelated process. Or in the boiler house itself, any high temperature hot water that depressurizes, for example, when we take that water out of the boiler to go to waste, any steam that's produced as a result of that water depressurizing, that's going to be reasonably clean. It's not going to have too many chemicals in it. So it's in a perfect condition for being diverted back to the hot well to help us elevate the water temperature that's there in demand for steam production. Not going to go through this too much. Suffice to say that if we've calculated the cost of steam, if we know that there's 25% of the total heat energy in the steam that is retained within the condensate, the steam tables tell us that, then we can apply the same calculation. 25% of the cost of steam is retained in the condensate. So if we calculated our steam at £100 per tonne, that is the value of the condensate. So we can calculate the payback in installing the appropriate condensate return system and ensuring that we get as much of that hot water back to the point of use as we can. Some processes, food, bev, pharmaceutical sector especially, they may elevate pressure and therefore the temperature of the water that's held in storage in what we call a pressurized deaerator. So if we can elevate that water that's in storage to 105 degrees, there's more energy in the water. Of course, we don't need to consume as much gas. We also don't need to consume as many chemicals. Therefore, we don't need to perform as much blowdown of the boiler. So the energy savings, the cost savings are coming to us from different directions. But it also means we've now got an excellent heat sink for all of those flash steam vents that were previously venting away to atmosphere. We can move one step closer towards a zero net loss steam system. And of course, if we've got steam condensate that is being dumped to waste through a fear of contamination, we can use a series of turbidity or conductivity probes. It really depends upon the nature of the contaminant in order to ensure that whilst that hot water is in a good condition to be used, we can do so. So it really comes down to closing that loop. One of the most important things we can do to ensure the steam system is working as efficiently as we can is by ensuring that we get as much of that vitally important hot water back to the boiler house for reuse. So takeaways really from today's presentation, please remember that rule of thumb. In a traditional steam system, we should be aiming to recover about 85% of the condensate so we can keep the temperature of the hot well at about 85 degrees. If either of those figures are significantly lower, then there's money on the table in terms of efficiency improvements. Please do bear in mind that condensate is only a single phase fluid when it's at a stable pressure. Whenever we've got a pressure drop, we are going to get that expansion. If that expansion is left unchecked, it's a significant inefficiency. But it also means that whilst that expansion is a necessary evil, we might perhaps want to investigate ways to see if that heat energy can be used in any other process. So that brings to an end today's presentation on condensate management. For those of you that are university students, please do take a snapshot of the QR code you can see in the bottom of the screen. It gives you useful information of our year in industry program, but also our postgraduate placements that we offer at Spirax Sarco. On that note, thank you very much for your attendance today. I look forward to presenting to you again next week, which is on the topic of steam condition, the causes and consequences of steam contamination. Please do feel free to make a comment on both mine and Brian's LinkedIn profiles with regards to this series of presentations. And if we have got time for any questions, please do drop them into the chat function. Over to you, Brian.
Okay, thanks, Dan. That's fantastic as usual. It's brilliant to hear about steam trapping and the fact that it's really important, a really important aspect. And what intrigued me was the sort of best case, or not necessarily best case, but rule of thumb of 2% losses in the system. We don't have any questions as yet, so I'll just finish summing up and see if any come in. And also the 6 degrees increase in the hot well give a 1% saving. I mean, that's fantastic. I came from an industry where the biggest cost to the manufacturer was materials. Second biggest cost was people, and third biggest energy. And I reckon with the changes in recent years, energy will probably be up to the second biggest cost. So if you can save 1% of that, that is fantastic. I do have a quick question. Dan, if you get flooding in a system, other than the obvious that the process is not going to be working great, are there any implications with the sort of downstream hardware?
If you've got flooding in the system, in the infrastructure, what we generally find is it's easy for an expert to diagnose when a steam trap has failed closed that's resulted in that flooding. It's not so easy for the site owners to demonstrate that, but they're more likely to get issues creeping up over time. So they're the mechanical issues, such as the erosion, the corrosion, the water hammer. We're more likely also to find that we get the steam, the energy content degrading and deteriorating. These are things that they're not as immediate as identifying when the condensate can't get away from a process. Because I'm trying to think of the example of domestic hot water heating system in a hospital. As soon as we can't get hot water, we know about it straight away. So we'll modify that steam trap, we'll repair it. There aren't necessarily any impact for capital equipment if the condensate doesn't get away. It creeps up on us over time, which can often be a bigger problem because there isn't that immediate diagnosis. Again, it's one of the reasons why we always encourage steam using sites to have those frequent steam trap surveys.
Okay, thanks for that, Dan. It's coming up to 7 o'clock. No other questions have appeared yet. I've seen. I'll have a quick look in the other chat. Can't see anything. So without further ado, you did spot earlier that I've lost the ability to count. So the next is the 6th lecture. Is that correct, Dan? Have I got that right?
That's correct. Yes.
Really? That's brilliant. And it is on Tuesday, the 22nd. That's next Tuesday at 6 o'clock. So Thank you, Dan. It was top notch as usual, and thanks to the Western Area IMechE Committee and the University of Huddersfield, and of course Spirax, Sarco, and look forward to seeing everybody next week. So take care and have a nice evening, and a safe journey home, Dan.
Thank you. Thanks all.
Thank
Cheers,
you.
guys.
Thank
Bye.
you very much. Bye bye.